Welcome. Today we're going to take a deep dive into inflammation. It's the body's fundamental response to any kind of injury, and it's a true double-edged sword. On one hand, it is absolutely essential for our survival, but on the other, it's the very same process that drives some of our most debilitating diseases.
So just take a look at these two images. On the left, we've got a scraped knee, a classic minor injury that's going to heal up in a few days. But then on the right, you see severely arthritic hands, a chronic, destructive condition that can cause a lifetime of damage. Now here's the fascinating thing. Both of these outcomes, the beneficial healing and the destructive disease, are orchestrated by the exact same biological process.
So that really begs the question, doesn't it? How can one single protective mechanism, something that's literally designed to heal us, lead to such drastically different, even destructive outcomes?
Well, the answer really begins with the word itself. Inflammation comes from the Latin word inflammo, which means to set alight. And that's a fantastic description, actually. It's this complex protective response that our body tissues launch against harmful stimuli, whether that's invading pathogens, our own damaged cells, or other irritants. Its whole purpose is a three-part mission. First, to eliminate the cause of the injury. Second, to clear out all the dead cells and tissue debris. And third, to kickstart the repair process.
Okay. Here's our roadmap for this explainer. We'll start with the fundamentals of inflammation. Then we'll compare the acute and chronic responses. From there, we'll look at the key cells and chemical signals, discuss the inflammatory fluid, and finally explore the different outcomes, from healing all the way to pathology. All right, let's start at the beginning. What is the initial spark that actually ignites this whole process? At its core, you can think of inflammation as a coordinated military operation. First, the soldiers are sent in to seek and destroy the threat. Then, a specialized cleanup crew arrives to remove all the debris from the battlefield. And only then do the engineers come in to rebuild the damaged structures. So how does this operation get triggered? This diagram illustrates it perfectly. Our resident immune cells, like macrophages, are studded with what we call pattern recognition receptors. These act like sentinels, and they're constantly scanning for two main types of alarm signals. The first are PAMPs, or pathogen-associated molecular patterns. Think of these as conserved structures on microbes, like components of a bacterial cell wall that our body instantly recognizes as foreign. The second are DAMPs, or damage-associated molecular patterns. These are different. They're molecules released from our own cells when they're stressed or dying, like ATP leaking out of a ruptured cell. The moment one of these receptors binds to a PAMP or a DAMP, the alarm is sounded and inflammation begins. Now, once that alarm goes off, the response can branch into two very different pathways. We have the acute response, which is like the first alarm, and the chronic response, which is much more like a long siege.
So the acute phase is the body's rapid reaction force. It's immediate, it's short-lived, and it's defined by these 5 classic signs. The heat and redness come from vasodilation, that's the widening of local blood vessels to ramp up blood flow. The swelling, or edema, is due to increased vascular permeability, which lets protein-rich fluid leak out into the tissue. And the pain is triggered by chemical mediators, like prostaglandins and bradykinin, that sensitize the nerve endings in the area.
The dominant cell type here, the first responders on the scene, are the neutrophils. You can think of them as the frontline infantry of our innate immune system. They're the first to arrive, flooding the site to phagocytose pathogens and clear away all the debris.
But what happens if that initial assault by the neutrophils fails to eliminate the threat? Well, the whole strategy shifts. We enter a long-term siege, and that's chronic inflammation. Here, the cellular players change. The key cells are now macrophages and lymphocytes, and the focus shifts from a quick resolution to long-term containment. The problem is, this chronic battle often leads to significant collateral damage, as the immune cells release enzymes and reactive oxygen species that also harm healthy tissue, eventually leading to fibrosis or scarring.
This table really summarizes the key differences beautifully. Just look at the contrast in onset, duration, the specific cellular players involved, and of course, the starkly different outcomes. It all really hinges on one critical factor: whether or not that initial threat is successfully and swiftly neutralized.
So let's take a closer look at the cells involved and the really complex system of signals that recruits them from the bloodstream to the exact site of injury.
This overview shows us the entire battlefield. You've got the blood vessels, which act as the highways for transport. You've got the various immune cells, our soldiers, circulating within those vessels. And you have the connective tissue matrix, which is the terrain where the battle will actually be fought. So how do these soldiers get from the highway to the battlefield? Well, it's a precise, multi-step process called leukocyte extravasation. First, the leukocytes begin to roll along the vessel wall, making weak connections via molecules called selectins. Then chemical signals called chemokines trigger a switch, activating high-affinity integrins on the leukocyte, which causes it to stick firmly to the vessel wall. Finally, the cell performs an amazing feat called diapedesis, or emigration, where it literally squeezes through the gaps between endothelial cells to enter the tissue and join the fight.
Now, one of the most visible results of all these vascular and cellular changes is the production of a specific kind of fluid, which really serves as the physical evidence of the ongoing battle.
This fluid is called exudate. And it's important to know this isn't just simple fluid like a transudate. An exudate is a protein-rich fluid that forms because of that increased vascular permeability we talked about. It's absolutely packed with crucial components, things like clotting factors to help wall off the area, antibodies to fight invaders, and of course, all the neutrophils and other immune cells that make up the response team.
And here we can see a really dramatic clinical example. What you're looking at is a cross-section of a lung with an abscess from pneumonia. That large, pale area the arrow is pointing to is purulent exudate, in other words, pus, and it's composed almost entirely of dead neutrophils and all the cellular debris they have ingested.
Finally, let's turn to the aftermath. What happens once the battle subsides? And, maybe more importantly, what happens if it never truly ends?
The body really has two main strategies here. If the threat is eliminated, the body begins the healing process by forming granulation tissue. This is basically a temporary scaffold, rich with new blood vessels and fibroblasts that start laying down collagen to repair the damage. However, if the enemy can't be defeated, think of the bacteria that caused tuberculosis, the body shifts to a containment strategy. It forms a granuloma. This is essentially a fortress made of immune cells, mostly macrophages, designed to wall off that persistent threat from the rest of the body.
This is where we connect the macroscopic evidence with the microscopic cause. On the left, you see the visible joint destruction in a hand with severe rheumatoid arthritis. On the right, you see the reason why. It's a microscopic view showing a massive infiltration of lymphocytes and plasma cells into the joint tissue. In this autoimmune response, these cells are mistakenly attacking the body's own tissues, releasing a flood of cytokines and enzymes that lead directly to the destruction of cartilage and bone.
And this reminds us of a really key point. Chronic inflammation isn't just an abstract process. It is the defining pathological feature of so many debilitating diseases where the body's own protective mechanisms have been turned against itself.
So, we are left with this critical paradox. Inflammation is a toolkit that is absolutely essential for our survival. But what happens when the tools themselves start to cause the damage? You see, the great challenge in medicine today isn't about eliminating inflammation entirely. We can't. We need it to heal. The real challenge is learning how to master its control, how to selectively dampen a destructive chronic response without disarming the vital acute response we depend on every single day.